So in this scenario, we have a projectile launch from the top of a cliff. So let's make this the top. And this is the vertical wall. And so if we go 30 degrees below the horizontal, that is the angle it's launched at. So what we know is there is a VZ to begin with, a VX to begin with. And after it's released, what we know is the only force acting on it is the force of gravity. So that means the only acceleration will be vertical. And X, or horizontal, is constant. So let's look for choices in these graphs that show a constant velocity. Now, if we look at the graphs, we've got displacement graphs, which are the first, and velocities that are the second. So we have to do two separate sets of Oizergas. So this one is the origin 0, 0, 0, 0, positive displaced, positive displaced. So we have the y-axis of delta x, the x-axis is t. So any questions about position or time, we will read off the graph. Delta x over delta t is the velocity. And the area is meaningless for an xt graph. So horizontally, we know the velocity is constant. The velocity is constant. And the velocity shows up as the slope. So we're looking for a constant slope. And so this is a positive constant value, but this is a 0, saying there's no horizontal velocity. So immediately we can take out choices C and D. Now if we look at the other set of graphs, we have the velocity, so OY, X, R, G, A. Y-axis velocity, x-axis time. We can read velocity and time. The gradient's delta V over delta T, which is the acceleration. And the area is V delta T, which is the vertical displacement. Now what we know is the velocity to begin with, vertically, there is a horizontal component that is negative and not 0. So if we look at these two just from the origin, we see this one has some negative value of V, and this says V0 equals 0 in the vertical. So this is out, and that's why 32 is choice A.